We can get going. So, welcome to another day of conference, maybe a Euro-friendly day of conference, given the timings. Let me just remind you, I'll paste it in the chat just in case you've forgotten. So in the breaks, we'll use this gather town to carry on discussion. So the Zoom will be closed. So if you do want to discuss, then I encourage you to use the gather town. Actually, quite a few of us using it the other day, and I think it works quite well. So yeah, please use it if you'd like to discuss further. So it's my pleasure to introduce Simon Riche from Clermont-Ferrand, and today he'll be talking about Hecke action on the principal block of a semi-simple algebraic group.
Thank you very much for the introduction, and thanks to the organizer for the invitation. And well, I apologize, I'm not participating in the special activities as much as I was planning to, but because of time difference, it's sometimes difficult. So today I'm going to talk about the construction of an action of the Hecke category on the principal block of a semi-simple algebraic group. And this construction is a joint work with Roman Bezukavnikov, and it answers a question that was considered in previous joint work with Jordi Williamson. So a different construction of this Hecke action has been discussed in the special seminar, but I guess not all of you I have attended this seminar, so I would try to recall some background on this question, but to be quick enough so that people that have attended this seminar talk do not fall asleep. So the question, well, the context for this construction is representations of reductive groups over fields of positive characteristic, but for this specific construction, it's convenient to assume the group is semi-simple. So I will consider K an algebraically closed field of characteristic P, which is assumed to be positive, and a simply connected semi-simple K algebraic group denoted by G. And as usual, I want to fix a maximal torus T and a broad subgroup B. And I will denote by W the Weil group of G with respect to T. So this is a finite group, and it's the choice of B determines structure of Coxeter group on W. And then I will consider the weight lattice X, the lattice of algebraic group homomorphisms from T to K star. And inside this lattice, I have the dominant weights X plus, and I will also need some notation for the root system, and I will denote this root system by R. And so the goal here is to say something about the combinatorics of the category rep G of finite dimensional algebraic G modules. And so, as was already mentioned in the talk of George Lustig on Tuesday, the important role in this description is played by the affine Weil group, which is the semi-direct product of the finite Weil group W with the root lattice. And the way we will see this affine Weil group here is via a certain action on the weight lattice, the dot action, which is defined by the formula, which is written at the bottom of the slide here. So in this action, the elements of the finite Weil group act by the row shifted action. So rho is the half sum of positive roots, and this plus rho and minus rho just shift the action by minus rho. And then the root lattice, so the lattice ZR, the lattice generated by the roots, they will act on the weight lattice by translation, but with a dilation factor of P, which is the characteristic of the field of coefficients. So as was already mentioned by George Lustig, the importance of this affine Weil group was first emphasized by Verma in the early 70s, and So to illustrate this action, it's convenient to look at a picture for a rank 2 group. So here I consider the case of the group SP4. So in this case, the torus has rank 2. So the weight lattice is a rank 2 lattice, and these are the dots, the green and red dots in this plane, which is the real vector space generated by the lattice. And the root system has, in this case, has 8 roots, which are these 8 black vectors. And so the red dots are the dominant weights, and the green dots are the weights which are not dominant. And in this plane, I have some hyperplanes. Here, the blue hyperplanes, which are the hyperplanes defined by the co-roots, so by the vanishing of the co-roots. And in the standard action of the Weyl group on this weight lattice, W appears as the subgroup generated by some reflections along these hyperplanes, which were on this picture, they are the orthogonal reflections. And in the definition of this dot action of the Weyl group, there is a first ingredient, which is that we shift everything by minus rho. So now this weight here is minus rho. And the finite Weyl group will act again as a subgroup generated by reflections, but centered at minus rho. And what we add on top of that is are these translations. So adding this translation is essentially the same as adding the conjugates of these previous flexions by these translations, and so we obtain some affine hyperplanes. So on this picture, I assume that p equals 5. If you want to have the picture for other values of p, you should dilate the hyperplanes, but without dilating the dots, which remain there. And so the affine Weyl group will arise as the subgroup will act as a subgroup generated by some reflections along these affine hyperplanes. And so there is a general theory of groups generated by affine reflections, and this example falls into this theory. And this general theory tells us that each of the alcoves, so this triangle will be a fundamental domain for the action of the affine Weyl group, and it also provides a Coxeter group structure on this group. So for this, I have to choose an alcove. So the most here there is a canonical choice of an alcove, which is the one which contains the weight 0. And once I have chosen this alcove, then I have a set of Coxeter generators, which are the reflections along the hyperplanes that meet the closure of this alcove. So when I said that I take the alcove that contains 0, well, it might be for small values of p that 0 is not in an alcove, but if you assume that p is bigger than Coxeter number, then 0 will be in an alcove, and usually I will assume that p is bigger than h, so that this makes sense. So I have this fundamental alcove, and this fundamental alcove gives so it's a fundamental domain for the action of the affine Weyl group. So in particular, the dots in the closure of this fundamental alcove are representatives for the orbits of the affine Weyl group acting on weights. So in this particular case, for SP4 and p equals 5, we have 12 orbits, which correspond to these the 12 weights inside this triangle here. So this, so one way to see this this structure in the representation theory was already mentioned by George Lustig, and it is as follows: for each dominant weight, we have an induced module n of lambda obtained by inducing the one-dimensional representation of the Borel subgroup defined by lambda to G. And in fact, so as explained by Verma and as mentioned by George Lustig, these affine hyperplanes here are exactly, well, the intersection with dominant weights are exactly the dominant weights for which this induced module has dimension divisible by P. But another way to see the importance of this affine Weyl group is in a statement which is in fact conjectured in this paper of Verma, which is called the linkage principle. To explain this statement, I have to recall the classification of simple G modules. So each of these induced module n of lambda has a simple suckle denoted L of lambda. And theorem of Chevalet tells us that this construction provides a bijection between dominant weights and isomorphism classes of simple G modules. And in terms of this classification, we have this linkage principle, which says that if the X1 group in rep G from L of lambda to L of mu is non-zero, then lambda and mu belong to the same orbit of the affine Weyl group. So as I mentioned, this result was conjectured by Verma. Then it was proved under appropriate assumptions by Humphreys, then by Carter-Lustig in case of GLN. And then there was an improvement on the proof of Humphreys using result of Katzos-Weiler. And finally, there was a completely general proof of, in fact, a stronger statement by Anderson after some preliminary work of Janssen. So for us, what this statement says is that the category of representations of G can be broken as a direct sum of subcategories called blocks, which are parametrized by orbits of the affine Weyl group on the weight lattice. So to each orbit C, I can associate a subcategory rep C of G, which is the Serre subcategory generated by the simples whose label belongs to C. And this gives me the composition of rep G as a direct sum of subcategories. So these subcategories are usually, often called blocks. Just for the experts, that's not a block in the strict sense, in the sense that some of these subcategories might be decomposable, but that's a different story. So I have this decomposition of the category rep G, and so in the case of SP4 in characteristic 5, we have 12 orbits for this action, and so the composition of the category of representations as a direct sum of 12 subcategories. And so the number of these subcategories will depend on P, because the number of orbits and the number of dots in this fundamental alcove will depend on P. But we expect, well, there are some expectations that these subcategories do not depend too much on P, and maybe I can say a few words about that later in the talk. But so now we want to describe these blocks, and well, there are some other instances of some other ways to make sense of the importance of the affine Weyl group. The most famous of which being the Lustig conjecture on characters of simple modules. But here I want to explain some results which can be seen as another way of continuing this idea by showing that in fact each of these blocks as a category can be described in terms of some data taken from the affine Weyl group. So for this, I need to introduce some other structure we have, which are the translation functors. The translation functors are some exact functors which allow to relate different blocks. So if I have two weights lambda and mu, I have a translation functor from the block corresponding to the orbit of lambda to the block corresponding to the orbit of mu. And this function, so I will not recall the construction precisely, but this functor is given by tensoring with a certain module and then projecting to a block. And as I explained before, if I assume that p is not too small, so p is bigger than constant number, then the weight 0 is in the fundamental alcove, and I will call principal block the subcategory attached to the orbit of 0, and I will denote it rep 0 of G. And we have a number of results that make sense of the idea that in this setting, if we understand the principal block, then we understand all of the other blocks too. So there is a way to describe the structure of these other blocks if we understand the principal block. And so in the rest of the talk, I will mainly concentrate on this principal block. So if I choose this principal block, then I cannot use the translation functors anymore because I don't want to go to another block, but I can still use some composition of translation functors. And in particular, I will use what I call the wall crossing functors, which are attached to Coxeter generators of my group, so simple reflections. And they are defined as follows. So recall that the Coxeter generators are in bijection with the walls of the fundamental alcove, so the hyperplanes that meet the closure of my alcove. And so for each of these hyperplanes, I choose a weight on the closure of the alcove, which is on this hyperplane. I will denote, well, I choose some weight mu s, and then I consider the functor of translating to this weight and then back to 0. And this composition will be denoted theta s. So it's well defined up to isomorphism. So, and it's a Nando functor of the principal block. And so what I'm going to explain next is, I can be roughly stated as saying that the principal block can be recovered from these functors. So to make sense of this idea, I will have to introduce the main tool that is needed to just state the result, which is the affine Hecke category. The affine Hecke category. So this is a special case of a general construction for Coxeter groups. And so before explaining what the Hecke category is, one has to recall what the Hecke algebra is. So again, that this is a general construction for Coxeter groups, but I'm only considering the case of the affine Wahl group here. So the affine Hecke algebra is a deformation of the group algebra of the affine Wahl group. So it's an algebra over the ring of Laurent polynomials with integer coefficients in a variable v. And it has a basis parameterized by the affine Wahl group. And the multiplication is determined by the rules that are written on the slide. So we have the quadratic relation for elements corresponding to simple reflections, and then the multiplication, the elements multiply as in the affine Wahl group if the length add. Well, so there is it is classical fact that these determine uniquely multiplication on this affine Hecke algebra. Okay, so the Hecke category will be some categorification of this algebra. So more precisely, the affine Hecke category will be Kroll-Schmidt k-linear monoidal additive category, the AF, endowed with the Noto equivalence parenthesis 1, which should be thought of as grading shift. Such that we'll recover the affine Hecke algebra when passing to the Grothendieck group. So this category, to the split Grothendieck group. So this category is additive, so it makes sense to consider the split Grothendieck group. And it is monoidal, so this Grothendieck group will be a ring. It has a ring structure. And we also have this autoequivalence parenthesis 1, which gives us some automorphism of this group. And so this split Grothendieck group becomes an algebra over Z bracket V inverse. And I want this algebra to be isomorphic to the affine Hecke algebra as an algebra over this ring of Laurent polynomials. And there is another important property that I will have a way to label indecomposable objects, or to parameterize the indecomposable objects by the affine Wahl group. So to each element of the affine Wahl group, I will associate some indecomposable object BW, such that any indecomposable object in the affine Wahl group will be isomorphic to a shift, a grading shift of such an object. And I mentioned in passing that this, the datum of such a category gives me a canonical basis for the affine Hecke algebra. More precisely, I assume that my category is Crouch-Schmidt, which implies that the split Grothendieck group has a basis consisting of classes of indecomposable objects. So these classes of the BW will give a basis of this Grothendieck ring as a module for Laurent polynomials. And so the definition of this category can be given in terms that are essentially independent of the ring of coefficients that I consider. Well, here I will only consider field coefficients, but I have this K which plays the role of coefficients. And the definition of the category can be made to be essentially independent of this field, but the description of indecomposable objects will depend in a very subtle and important way on the choice of coefficients, more precisely on the characteristic of the coefficients. And if this characteristic is P, as I want to consider here, the corresponding basis of the affine Hecke algebra is called the P-canonical basis, and is denoted in this way with this PH underline. So this P-canonical basis will come back later in the talk, but for now, I will first need to explain how this affine Hecke category is constructed. So in fact, it can be constructed in several equivalent ways. So the first incarnation of this affine Hecke category, which is the easiest one to state, but which is not the most useful one for our approach of this problem, is as a category of parity complexes on the affine flag variety. So I will briefly mention this construction, this incarnation, but this is not so important for what I'm going to discuss next. So for that, I will have to consider well, essentially the Langlands-Ewald group. Well, not exactly the Langlands-Ewald group, but the simply connected cover of the Langlands-Ewald group, which is this G triangle. And I will choose some Borel subgroup in this group G triangle. And then I can associate to this group its grouping scheme, its loop group, which is a grouping scheme, and then the arc group, which is a group scheme. And and inside this arc group, I have the Iwahori subgroup. And if I form the quotient, I find an int variety, which is the affine flag variety. And on this affine flag variety, I can consider the Iwahori equivariant Dirac category with coefficients in K. And in this category, we have a very nice class of objects, which are the parity complexes. And well, I have a convolution product on the I equivariant Dirac category, which restricts to a convolution product on parity complexes. And this gives me a additive monoidal category, which is one possible incarnation of the affine Hecke category. And in this case, the classification of objects, of indecomposable objects, is part of the general theory of parity complexes. And so I have one for each orbit of the Higori subgroup on this affine flag variety. So this is indeed parameterized by the affine Weyl group. So this is the first incarnation of this Hecke category, but there are other incarnations which are important and which will be more relevant for this talk. So the second incarnation is in terms of a diagrammatic category introduced by Elias and Williamson. So for this, we start with a category which is not additive, which is just a k-linear monoidal category, whose objects are words in simple reflections, and whose morphisms are defined by generators and relations. So there is a family of generating morphisms, which are of 4 different kinds. So first we have these polynomial boxes. So these boxes with a label, which is an element in the symmetric algebra of the k-vector space associated with X. And so this is a morphism from the object corresponding to the empty word to itself. Then I have these dot morphisms, which are morphism from the object corresponding to one simple reflection to the empty word. Then I have these trivalent vertices and these more complicated morphisms, which are associated with pairs of simple reflections. And these morphisms are subject to a number of relations. So some of them are written here. There are more relations. Well, these relations, well, so they might seem easy at first sight, but well, in practice, it can be quite hard to work with these relations. But anyway, anyway, the precise form of the relations will not be so important for what I'm going to say. So I should say a few words about where this definition comes from. And in fact, it comes from the theory of Zögel bimodules. So there is a different kind of category that one can attach to a Coxeter group, which is so the category of Zögel bimodules. And so the initial data for the definition of Zögel bimodules is, in addition to a Coxeter group, is a representation which satisfies certain technical conditions. And if we have such a representation, then Zögel explained how to define a very nice category of bimodules over some symmetric algebra. And so this category defined by generators and relation was found when the Elias and Williamson were looking for a description of this category of Zögel bimodules in terms of generators and relations. So they found such a description, and what one sees with this description is that the category defined by generators and relations makes sense even when the assumptions that Zögel makes are not satisfied. And so this allowed them to define some replacement for the category of Zögel bimodules, even without these technical assumptions that Zögel has. And this is very important for us here, because this is the setting of the affine Weyl group that I consider here typically does not satisfy Zögel's conditions. So, well, in fact, I've explained. So I briefly explained how to define this category, this Elias-Williamson category. So this is a category which is not which is not additive, but then we can formally add these direct sums and then take a Karoubi envelope, and then one gets a category which turns out to be equivalent to the category of parity complexes. So this is another way of constructing this affine Hecke category. So this is a very nice definition, and this is the point of view that we considered with Jordi Williamson when we first considered the question that I'm going to discuss next. But it turns out that it's not really easy to work with this definition for the problem we have, and the incarnation of the affine Hecke category that we will really work with is a third incarnation, which was found recently by Noriyuki Abe in terms of some enhanced Zergel bimodules. So what Abe did is to give a description of this, well, more generally of the Elias-Williamson category in terms which are similar to the usual description of Zergel bimodules. So we again have this algebra R, which is the symmetric algebra of the K vector space associated with my weight lattice, and I will denote by Q the fraction field of R. And so as in Zergel theory, one considers some category of graded R bimodules, but what Abe understood is well, so what was clear before was that that Zergel theory, well, does not behave in an appropriate way for when these technical conditions are not satisfied. But what Abe understood is what needs to be added so that the theory behaves as it does in the usual Zergel theory. And this data that one needs to add is a decomposition of the tensor product of the bimodule with Q on the right, a decomposition of this tensor product parameterized by the affine Wahl group. So more general for parameterized by the Coxeter group under consideration. And we add certain technical assumptions. So we want M to be flat as a right R module. We want that this decomposition has only finitely many non-zero terms. And we want that on the summand corresponding to W, the left and right action of the algebra R differ by the action of W. So typically, one of the conditions that that Zergel had to impose was that the action of the Coxeter group on the representation is faithful. So in some important instances, the action will not be faithful, just like in the example that I consider here. Well, in this example here, the action of the affine Wahl group on R is just obtained from the action of the finite Wahl group by the natural quotient from the affine Wahl group to the finite Wahl group. So the action on so the action of the group on R, well, the action of an element of the affine Wahl group on R does not determine this element. And so essentially what Abe explains is that one should remember not only the action on R, but really the element. So this is well, one way to interpret this additional data of this decomposition parameterized by the affine Wahl group. So this category has a natural monoidal structure given by tensor product of bimodules. And for each simple reflection, we have a distinguished object BS in this category, which has underlying graded bimodule given by the tensor product of R with itself over the S invariance. And well, so there is a natural decomposition of the tensor product with Q, where there are two non-zero terms corresponding to the identity element and to S. And then one considers the subcategory generated by such objects under tensor product, direct sums, grading shift, and direct summands. And one obtains in this way a monoidal category. And what Abe showed is that this category is again equivalent to the same affine Hecke category. And so this is the incarnation that will be most useful for what I'm going to discuss next. Okay, so now I can finally come to this Hecke action on the principal block. So for that, we assume that P is strictly bigger than H. And so the main theorem of this paper with Bezukavnikov is that there exists an action of the affine Hecke category on the principal block rep 0 G, such that the object corresponding to a simple reflection S acts by this wall crossing functor theta S. So I should say a few words about why we care about having such an action. So I will try to come back to this at the end of the talk if time permits, but I will just briefly mention this already, that in fact, if we know that there exists such an action, then we know the structure of the well, we obtain a concrete description of the principal block. More precisely, we obtain a description of the category of tilting objects in the principal block as the antispherical quotient of the affine Hecke category. So the quotient of the affine Hecke category by the subcategory generated by indecomposable objects whose label is not minimal in the corresponding coset for the finite Lie group. Well, so I will try to explain, to say a bit more about why having the action is sufficient to deduce this equivalence. But in particular, once we have such an equivalence, we can get a character formula for tilting modules and also for simple G modules. And again, I will say a few more words if I have time at the end of the talk. So this the existence of such an action was conjectured in joint work with Jody Williamson around 2013. And when we first thought about that, what the incarnation of the Hecke category that we had in mind was the diagrammatic incarnation in terms of generators and relations. And if we, well, in terms of this description, we know how we want the elements corresponding to simple reflections, how we want these objects to act. So this gives the action of any object of the category. And then if we want to specify such an action, we have to define images of the generating morphisms and check that these functors satisfy the appropriate relations. And we first thought that it could be doable to do to define such functors and check the relations. But this turned out to be much more complicated than what we expected. So in the special case of the group GLN, one can indeed follow this strategy. And this is what we did with Jody Williamson using it relies on the Kavanagh-Rouquier theory of two-Kac-Modi algebras. And well, in fact, there was another proof also based on these tools, but arranged in a different way by Elias Lozev around the same time. And but for a general group, we don't have such a structure. And so, in fact, what we first managed to prove is not the existence of the action but rather its consequences. In particular, the character formula for tilting modules, and it was proved in joint work with Pramod Acharya, Toru Makisumi, and Jody Williamson. And so now we do have a proof of the construction, of the existence of this action. And in fact, in parallel, there was another proof that was found by Josh Schiapara, which was discussed in this special year seminar and which appeared on arXiv earlier this year. So now I will try to explain how one can construct this action. So the construction uses representations of the Lie algebra of G. So I will denote by German G this Lie algebra of G, and by T the Lie algebra of T. And to say how this works, I have to recall the description of the center of the universal enveloping algebra. So under our assumption, the center has a very nice description. So there are two central subalgebras that are easy to describe. Well, first, the Harish-Chandra center, which is defined as the G invariance in the enveloping algebra. So this is similar to the description of the center in the similar setting of characteristic 0. And as in characteristic 0, we have a Harish-Chandra isomorphism, which describes this subalgebra as functions on the quotient of the dual of T by the shifted action of the Val group, of the finite Val group. So this is one central subalgebra. And there is another central subalgebra, which is called the Frobenius center, which is the subalgebra generated by the elements of the universal enveloping algebra of the form x to the p minus x bracket p. So here x is an element in the Lie algebra, x to the p is the pth power in the enveloping algebra, and the x to the bracket p is the restricted pth power. So the operation that we have on the Lie algebra of an algebraic group, of any algebraic group defined over a field of characteristic P. So these elements are central, and they generate a subalgebra which is isomorphic to functions on the Frobenius twist of the dual of the Lie algebra. So if you don't know about Frobenius twists, you can forget about this parenthesis one. This is just a twist of the structure of this scheme as a scheme over the field. But anyway, we have these two central subalgebras, and in fact, the center is generated by these two subalgebras. And in fact, it is isomorphic to the tensor product of these two subalgebras over these intersections, over the intersection. So geometrically, the Frobenius center is functions on essentially the dual of the Lie algebra. The Harish-Chandra center is functions on the quotient of T star by the Val group. And the intersection is the quotient of the dual of T by, the Frobenius twist of the dual of T by the Val group. And so we obtain a description of the center as functions on this fiber product. And well, for this construction, I will have to work with some completions. And more precisely, the Harish-Chandra center, so it's functions on this quotient. So the maximal ideals in this quotient, in this Harish-Chandra center, are given by W orbits in T star. And I will be, in fact, only interested in the elements of T star, which are obtained as differential of a weight, of a character of T. So given a weight lambda, I have a maximal ideal defined by the image of the differential of lambda in the quotient of T star by the W by the Val group, and I consider the completion with respect to this ideal. And I will denote by UG lambda hat the tensor product over the Harish-Chandra center with this completion. And I will consider algebras which are defined similarly, but now for UG tensor UG opposites over the Frobenius center. So in this case, I have two copies of the Harish-Chandra center coming from the left and the right factor. And I can tensor with completions for both of these subalgebras, and I obtain an algebra which will be denoted U lambda hat mu hat. So essentially, these modules over this algebra are certain bimodules over UG. And why do I care about these algebras? It's for the following reasons. I can consider the category of G-equivalent modules over this algebra UG0 hat. And this category will contain the category, the principal block, in fact. So here, if I have a representation in the principal block, I can differentiate the action of the group to get an action of the Lie algebra. So this will give me some G-equivalent UG module. And if I start with something in the principal block, then the Harish-Chandra character will generalize character 0. So it will define for me a G-covariant module for this this completed algebra. Now, on the category of modules for this algebra, I have an action of a certain category of bimodules. So in fact, of G-covariant modules for this algebra U0 hat, 0 hat, which act just as bimodules act on the categories of modules. And so I can, so I have this monoidal category which acts on this category containing the principal block. And in fact, the word crossing functors are given by actions of certain objects of this monoidal category. So more precisely, these translation functors, they are defined by tensoring with certain G module and then projecting to a block. So tensoring with a G module is the same as tensoring with the, well, easily defined bimodule, and then projecting to a block is realized by just tensoring with some completion of the Harish-Chandra center. So I have these objects of the category U0 modules over U0 hat 0 hat, which realize word crossing functors. So if I want to prove the theorem, I just have to construct a modular functor from the Hecke category to this category of bimodules, of equivalent bimodules. And I know where to send the object BS. It should be sent to this bimodule, which realizes the action of the corresponding word crossing functor. So this is what we're going to do. And we will use two important technical tools. First, the constant section. The constant section is a section of the adjoint quotient, usually. Here, I want rather to use to consider the co-adjoint quotient. So I have this quotient G star mod G, which identifies with T star mod W. And the quotient from G star to this G star mod G has a nice section, which is defined by an affine subspace in G star, which is contained in the regular locus. So this construction is classical for characteristic zero coefficients, but it also works under very mild assumptions in positive characteristic. And so we have this section of the adjoint quotient consisting of regular elements. And the other technical tool that we will use is a certain group scheme over this constant section, which is the universal centralizer. So this is a smooth affine group scheme over this constant section, whose fiber over an element xi is given by the centralizer of xi for the coadjoint action. So in terms of these things, we will define certain algebras and certain group scheme. So first, I have this algebra U lambda hat mu at S, which is obtained as follows. So I start as before with my algebra UG tensor UG up over the Frobenius center. Then I restrict to the constant slice. So remember that the Frobenius center is functions on the Frobenius twist of the dual of G. So here I consider the Frobenius twist of the constant section, which is an affine subspace in this Frobenius twist of G star. So I just tensor with functions on this constant section. And then I complete with respect to the ideal defined by lambda and mu in the Harish-Chandra center. So this is this algebra US lambda hat mu hat. And this algebra has a central algebra, central subalgebra coming from the center of this tensor, well, the center of UG. And so this subalgebra will be denoted ZS lambda hat mu hat. So it is a completion of function on this fiber product. And finally, I will consider an affine group scheme over the spectrum of this algebra, which comes from the universal centralizer, More precisely, I have the Frobenius twist of the universal centralizer, which is a subscheme in G1 cross S1. Then I pull back to G, and then I pull back on the base from S1 to the spectrum of the S lambda hat mu hat, and I obtain some flat affine group scheme. And using these tools, we have two main steps in our construction. The first one is to show that restriction to the constant section is fully faithful for the modules we care about. So I have this category of G equivalent modules over this completed algebra U lambda hat mu hat. And restriction to S gives us a functor to modules over the similarly defined algebra for S, which are equivariant with respect to the group scheme that I just defined. And this restriction functor is fully faithful on the modules that appear when considering translation functors. And so this is the first result that we prove. This is based on some very classical observation that representations are, that equivalent coherent sheaves on the regular part of G star are the same as representations of the universal centralizer. Okay, so to understand this category, we just have to look at the restriction to the constant slice. And then the second important result that we need is some localization theorem. So it describes the category of equivalent modules for this algebra US lambda hat mu hat in terms of representations of the associated group scheme. So this works in general when we consider a pair of weights which both belong to the lower closure of the fundamental alcove. So this result is reminiscent of the general localization theory for representations of Lie algebras in positive characteristic due to Bezukavnikov, Mekovic, and Ruminin. And our proof is based on the same tool. In particular, the same tools, in particular, the fact that the restriction of the enveloping algebra to the constant slice is an Azomaya algebra. So more generally, when you restrict to the regular locus, it's an Azomaya algebra. But well, we do not rely on the existing theory, essentially because we want to consider equivalent modules, and well, it's not so easy to work equivalently with the localization theory. But on the other hand, we have two important properties that are there here and which are not there in the general theory. The first one is that we consider some category of bimodules and not modules, which simplifies things. And also that we only care about what happens on the constant slice and not on the whole Frobenius center. And so this also simplifies the situation a lot. And so we have some explicit construction of such an equivalence. And then we can finally introduce, use what is provided by Abe's incarnation of the Hecke category. And the main thing one has to realize is that the data in Abe's category are essentially equivalent to the data of a representation of this group scheme constructed out of the universal centralizer. We have the universal centralizer over, which is a group scheme over, well, the Frobenius twist, which is a group scheme over T star 1 mod W. And then we pull back on both sides to T star 1. And and then we consider some category of graded module graded representations which are flat, which was satisfy a certain flatness assumption. And this category will turn out to map fully faithfully to Abe's category. And essentially, well, and the relation between this description and the data in Abbe's definition is as follows: that the universal centralizer is a flat group scheme, and so the flat to define well, if we care about flat modules, the data of such a representation is determined by its restriction to some open part. And so here we can restrict to the regular semisimple part, and in the regular semisimple locus, the universal centralizer is just some torus. And so essentially the decomposition in Abbe's and hence by modules comes from the fact that we have representations of some, that generally we have representations of some torus, and the data of representation of a torus is the same as data of a grading, which is part of what appears in this direct sum decomposition. So we have such a functor, such a fully faithful functor, whose essentially image contains the image of the Hecke category. So we can work with this category of representations. And this category of representations, via some completion procedure, we can map it to representation of the group scheme that appears in this localization theorem for modules over US 0 hat 0 hat. And this completion procedure, well, so the scheme that appears in this description is not exactly the same as the one which appeared in the localization theorem, but these schemes are related by some étale maps. So when you complete, you don't see the difference. And so this gives us a monoidal functor from the Hecke category to our category of US 0 hat modules. And then one has to understand what is the image of the objects BS under this functor to check that they correspond to these wall crossing by modules, which will complete the proof. Okay, so my time is almost over. So I just want to make some brief remarks about these results. So as I promised to say a few words about the character formula when it gets in this way. So for this, I have to introduce the peak agentic polynomials, which are the coefficients one obtains when expanding elements of the peak canonical basis in terms of the standard basis. And in terms of these Diagnostic polynomials, we have a formula which expresses the classes of tilting modules in the regular block in terms of induced modules in the regular block, and the coefficients are some values at 1 of some expression given in terms of the peak agentic polynomials. So this formula is a corrected version of an earlier formula conjectured by Andersen, which was itself inspired in particular by Lustig's conjecture on characters of simple modules. Okay, I was planning to say a few words about why you having the action is sufficient to provide such a character formula, but I don't think I have time for that. But this is also related in some way to the Finkelberg-Minkowitz conjecture, but I don't have time to talk about that either. But I just want to mention a few words about another topic which was discussed in the special year seminar, which is this two realizations equivalence due to Bezukalnikov, which relates the two natural categorifications of the affine Hecke category, one in terms of perverse sheaves on the affine Clark variety, and the other one in terms of equivalent coherent sheaves on the Steinberg variety. And so this equivalence was constructed by Bezukalnikov for characteristic 0 coefficients. And it is a project of Bezukalnikov with Laura Ryder and myself to construct some counterpart of this equivalence for positive characteristic coefficients. And so even though this, what I just explained is not really part of this project, but it's not unrelated either. So so I have explained how Abe's incarnation of the Hecke category gives a modular functor from the Hecke category to certain category of representations of this group scheme constructed out of the universal centralizer. And in fact, the category of representations of this group scheme is equivalent to equivalent coherent sheaves on the regular part of the Steinbeck variety. And so the construction of this functor points towards a coherent realization of the Hecke category, meaning a description of the Hecke category in terms of some category of coherent sheaves on the Steinbeck variety. Except that here we only considered the regular part, and one has to pass from the regular part to the whole category. And well, this requires some work which still has to be done. But in the end, it should this coherent realization of the Hecke category should be the coherent counterpart of the description of the Hecke category in terms of tilting perverse sheaves on the flag on the affine flag variety. More precisely, tilting objects in Yun's completed version of the derived category of sheaves on the affine flag variety. Okay, thank you very much for your attention.
Great, thank you very much, Simon, for your talk. Does anyone have any questions?
I guess I had a question, which is, what is the motivation for the conjecture originally?
So the motivation was the character formula. So we were trying to understand. So so when we started, so there are two famous conjectures in this context, which is the Lustig's character formula, which gives conjectural character formula for simple modules, which is now known to hold in large characteristic. And there was this other conjecture by Andersen on characters of tilting modules. And when we started thinking about that, well, Jordi had just found his counterexamples to Lustig's conjecture, showing that the conjecture does not hold for some interesting characteristics. And so we were trying to think about how to find a replacement for Lustig's character, and we had this idea that the combinatorics that should provide this replacement well should be this p-casuistic combinatorics. And so we were trying to see how to find this this formula for simple modules, but it turned out that it's not so easy to modify Lustig's conjecture in appropriate way. And what we understood is that it was easier to well, it was better to modify Andersen's conjecture, in fact. And so this conjecture is, well, has to do with the fact that it is standard that the Gartning group of the principal block is a module for the group algebra of the affine group, and in fact it's the antispherical module with for an action defined in terms of word crossing functors. And so we have this, and in fact these coefficients here, there are some antispherical Cauchy-Janoschik polynomials. So there are some polynomials that naturally appear in this antispherical module. And so so we understood that this formula should be thought of as saying that that this is some combinatorial shadow of the fact that the principal block is the categorified antispherical module. And so this is the equivalence that was okay. No, it's on the same slide also. And so this well, so the equivalence between this quotient and the and tilting modules in the principal block, and then so our motivation was to get this description.
Great. Are there any more questions?
I just
Well,
don't, sorry. I just don't understand exactly what's like Abbe's condition that there's this fixed splitting after you localize. Like, how do I see this from the coherent thing you were writing down?
So yes, I was probably too quick when I tried to explain that.
No, I don't know. Yeah.
So these are so the affine Val group is made out of two pieces, which one is the finite Val group and the other one is the root lattice, and so the decomposition in terms of the Val group comes from the geometry that we are considering some representations of a group scheme over T star cross T star over the W quotient. And so in fact, if I have any and so this fiber product, when we restrict to the regular semisimple locus, it's just a number, well, W many copies of just of T star. And so if I start with any coherent sheaf on this, and I restrict to the semisimple log, a regular semisimple locus, then I get some decomposition according to the finite Val group. And the direction of the root lattice comes from the fact that the universal centralizer is just each centralizer is just a torus over the regular semisimple part, and so I get this root lattice decomposition out of this torus action, and combining the two things gives the decomposition in terms of the affine Val group.
If you wanted to do this for a finite Val group, though, right? Like you don't, if you want the Hecke category before localizing, you can't just say, oh, I'm working over some regular locus. I don't, is there an analog of this for the finite Val group?
Well, for the finite Val group, we just need this fiber product. I mean, there is nothing to say about the.
Yeah, but then you're not automatically over the regular semisimple locus.
But well, Abbe's the data in Abbe's category is just a decomposition of the tensor product with the fraction field. So you just have to have a decomposition generically. So.
Well, maybe I can add a comment. So the way I understand it is that, we're trying to model this kind of union of graphs, which is not, as Simon said, so it's, we should not be thinking of it as sitting inside the square, but we take the formal union over, start with the joint union over the affine Val group, and then glue things along certain hyperplanes. But this Abbe's trick is that you can describe this in a simpler way because I guess locally at every intersection point, I think you still have an embedding into the square. So essentially this, so you can think of this as a sheaf on the square with some additional data, and this additional data is enough to give generically.
What's the additional data?
Well, again, this so this abstract union of graphs that I described, it still maps to the actual union of graphs, but there have
also some sort of descent data.
That well, we describing the shift upstairs in terms of shift downstairs, just a direct image, and then this kind of additional lifting data, it's enough to give it generic.
Okay, that helps. Thank you.
Okay, well, maybe we can have more discussions in Gathertown if people want to carry on probing Simon for more information. But yeah, let's thank Simon again for his wonderful talk.